Test. Oh, cool. Awesome. All right. Well, my name is Sean Bowe. I'm a cryptographic engineer working for the Electric Coin Company. And today I'm going to be talking about SONiC, which is a new ZK SNARK that I've developed alongside Mary Meller, Markov Kohlweiss, and Sarah Michael John. In retrospect, the title of the talk doesn't really make that much sense. It should probably be Trustworthy SNARK Setups. For the last few years at the Electric Coin Company, I've been working on trying to make these setups more robust and more secure and more trustworthy. A lot of people are trying to eliminate trust entirely, but I think that it's sort of, for a lot of protocols, the performance that we get out of parameter setups is just too good. And so we're going to be stuck with them for a while. So making sure that we do these setups in a trustworthy way is really important. And so a lot of those efforts have culminated, at least partially, in SONiC. So SONiC is a ZK SNARK, which means it's a generic computation zero-knowledge proof of knowledge. It's fast to verify and has small proofs, so it's succinct. And it's the best kind of succinct because it has constant size proofs and constant verification time. But as with all SNARKs that have these properties, it requires a parameter setup. So we have to perform some kind of trusted setup of some kind. Now, most SNARKs, at least all the SNARKs that have these or all the previous SNARKs that would have these properties before, you would have to encode the circuit into the parameters. The parameters were specific to a circuit. And so you'd have to perform a new setup every single time you want to use a different circuit, which is just ridiculous logistically and increases, obviously, the surface area of attacks. So ideally, we'd like to have universal parameters, and that's what SONiC is all about. It's a single set of parameters. It requires a trusted setup, but there's only one setup for all circuits up to a certain size bound. Also, SONiC's parameters are updatable, so the setup never really ends. It can just continue accumulate randomness over time. It never has to stop. And so I think the combination of the universality and updatability makes for the most robust and secure setups that you can possibly do with SNARKs. So we weren't the first paper to introduce this concept. This came out of a paper last year from Jens Grot and some of my other co-authors, which introduced a scheme with these properties. But unfortunately, it had quadratic size parameters. So even if you had a circuit kind of the size of the ones that we use in Zcash, that's just too big of size of parameters. So it's completely impractical. So SONiC is the first actual practical instantiation of this sort of protocol because we have linear size parameters, and so it works out. So I wanted to talk about how SONiC works in detail, which I don't know if I have enough time to do, but I'm going to try to do it by talking really fast. So we'll see if that works out. So I'm going to actually talk about how SONiC works in the abstract by treating all the components that it needs as sort of a black box. So all SONiC really needs is a polynomial commitment scheme. So what is that? Well, it's a scheme that allows you to take a arbitrary univariate polynomial and commit to it. Then you can evaluate that polynomial and then prove that you evaluated it correctly. Ideally, actually, we also require that there should be some guarantee about the actual degree of the polynomial that was committed, but that's all we really need for that. There's a couple other requirements. Obviously, in order to make a SNARK, we need the polynomial commitment scheme to actually be succinct. So the commitments in the opening proof should be small. The verification procedure should be fast, asymptotically speaking. For zero knowledge, we need the commitments and we need the opening proofs to reveal as little as possible about the underlying polynomial because we need one of these polynomials eventually is going to end up being one in which contains witness information that the prover is trying to keep secret. So those are the only requirements for a polynomial commitment scheme. I'm going to assume that our commitment scheme has some other properties. We can get around these properties or we can build a commitment scheme easily with these properties, so it's not really that interesting, but it helps if our commitment scheme is additively homomorphic, so we should be able to scale the commitments and add them together. We'll be working with Laurent polynomials with the negative exponents, and it should be cheap to demonstrate that the committed polynomial has a constant term of 0. So let's just assume that we can do this and do these sort of things with our polynomial commitment scheme, and we can create SONiC, and that's all we need. So most of the people in the audience that have worked with ZK SNARKs or either implemented things using them or worked with them directly are familiar with rank 1 constraint systems, which are just a way of arithmetization for an arithmetic circuit so that we can describe the circuit in terms of a set of equations. This is kind of a terse way of explaining what R1CS is, but it's basically you have some variable assignment, which consists partially of public inputs and partially that the verifier knows and partially private inputs that the prover knows. And we have a bunch of fixed linear combinations multiplied by other fixed linear combinations equal other fixed linear combinations. And this generalizes enough that we can express anything. So we do something different in SONiC. We base our paper on an arithmetization from a paper that precedes bullet proofs. In this, we have 3 vectors of length n that the prover knows. It's the witness assignment. And we have a q-length vector, k, which is the instance of the public inputs that the verifier is enforcing. And then we have 2 sets of constraints, multiplication constraints and linear constraints. And the multiplication constraints, just kind of simulating the multiplication gates in a arithmetic circuit. So entries in A multiplied by corresponding entries in B equal entries in C. And then we have linear constraints where some fixed linear combination of all of the elements in A, B, and C are set to equal some element in K. So just like in R1CS, when we're trying to collapse all this down into a single succinct argument, we're going to collapse, we're going to use different techniques for this arithmetization. We're going to collapse all of the multiplication constraints into a single equation by introducing a new formal indeterminate y. So basically we're embedding all the constraints into different coefficients of a polynomial. And if we were to evaluate this polynomial at a random point, and this equation would be satisfied, then we know with high probability that the constraint, all of the multiplication constraints with high probability would be satisfied. We can do the exact same thing with the linear constraints. It's a little small, but I promise you can do it. And you can collapse it all into a little bit prettier equation once you introduce a few helper polynomials that I've listed on the bottom there. The u, v, and w polynomials are fixed for a given circuit, and the k polynomial is fixed for a given, well, not fixed, but it's derived from the public inputs. So the general technique is for having the prover commit to A, B, and C the A, B, and C vectors, and then checking at a random point if this equation is satisfied, or namely that the left-hand side is equal to 0. So what we're going to do is we're going to borrow, again, another technique from that paper where a special polynomial t has as the constant term twice the left-hand side of the equation above. And so what this means is if we can demonstrate that the constant term of that polynomial is 0, then with high probability the constraint system is satisfied. So the other polynomials, we have this R polynomial that consists only of the witness, and then we have this S polynomial, which is just as fixed polynomials from earlier. So this S polynomial is fixed. And to see why this T polynomial has a constant term that's twice the left-hand side, just look at the individual products. You'll see that, for example, the exponents of y, that should be backwards on the S polynomial, but the exponents are kind of canceling each other out to influence the constant term. Same thing with the B terms and the same thing with the C terms. When the R polynomial is multiplied by itself as part of this product, it ends up producing actually 2 times because it multiplies A and B twice, so this is the reason why we scale the polynomial. But we basically get exactly what we want, and so that's the strategy. SONiC changes things around. We move the exponents around a little bit to make it easier. But one of the most important changes we do, well, I guess for performance reasons, is that we've ensured that the R polynomial can be committed to using a univariate polynomial commitment scheme. You'll see that we've modified it so that all of the exponents of x correspond with exponents of y in all the terms. And why is this important? Well, x to the I times y to the I is equal to x times y to the I for all x and y in the field. And so we can use a univariate polynomial commitment scheme to commit to R. So in the course of this modification, what we've accidentally done, because of this A and B product happens twice, but the first time it happens with y, and the second time it happens with 1, in the way we've arranged it. So we end up with both positive exponents of y and negative exponents of y. But this is the same as if we had actually embedded all the constraints into negative exponents of y redundantly as well in the first place. And so that's totally fine. So we do this, and we modify the w polynomials to compensate for the change, and then we end up with what we have. So the general strategy is for the prover to commit to the R polynomial and to to send that commitment to the verifier, and the verifier is going to choose the challenge y. And then the prover is going to commit to the t polynomial with x unknown, and then send that to the verifier, and the verifier will choose x, and then we'll start opening up the r and t polynomials. So the point of committing to the t polynomial is the commitment scheme for free gives us the ability to determine that the constant term is 0. And so now all we're trying to do is ensure that the t polynomial commitment is correct and it's consistent with the original r polynomial. So the verifier is going to have to evaluate the s polynomial and the k polynomial itself. It performs, asks the prover to open the r polynomial commitment at x and x and y, or x times y, and the t polynomial at x, or t commitment at x, and then checks to make sure everything's consistent. And there you have proof of knowledge. In order to get zero knowledge, all we really have to do is add some blinding factors to the r polynomial, so I'm not going to go into that. Well, with additively homomorphic polynomial commitments, which are the ones that we were working with in SONIC, the commitments, we can actually do a little bit better because we can send the openings for commitments that are being opened at the same point, namely r and t get opened at x at one point. So we just do a random linear combination of the commitments and the openings and then open them at the same time. And so this ends up with 2 commitments, 2 openings, 2 opening proofs, and 2 field elements. So that's pretty small, but it's not succinct because this s polynomial has to be evaluated by the verifier. It's a bivariate polynomial, and it has a linear number of terms in the number of gates in your arithmetic circuit. And so we came up with a few different techniques for amortizing away or eliminating the cost of evaluating this s polynomial. They all are dependent on the fact that the s polynomial is fixed for a given circuit, which is usually the case with SNARKs because we're doing these parameter setups and embedding the circuits anyway. So the 3 techniques are as follows. The first one is not very interesting. It's basically if you have the same prover creating 2 proofs with the same circuit, well, then they can run the protocols in parallel. Then you end up with the same challenges y and x, and the verifier just has to evaluate the s polynomial at one point. And so that's really easy. But actually, we can do a little bit better. The t polynomial commitment itself, actually, between all the proofs can be shared because we're only interested in the fact that, first off, it's consistent, and second off, that it has a constant term of 0. And we could do something similar with the fact that the openings can be shared because they're being evaluated at the same points. Within a proof, we can do the same thing through multiple proofs. And so what we have is a marginal cost of 1 group element and 2 field elements for a single proof in this setting, which is really interesting. I'm not aware of anything better in the literature for that purpose. But that's not very interesting in practice because usually you're more interested in multiple provers having constructed multiple proofs independently of each other. They've disappeared, and you want to somehow still get some kind of amortization of the cost of evaluating the polynomial. So the second technique that we introduce, let's say that we have 3 proofs, again, the same circuit, and so therefore the same s polynomial, but they're being evaluated at different points because they're completely independently created. The provers are long gone, so what do? Well, we're going to have some outside entity come in, and we'll call it a helper or whatever you want to call it, and they're going to commit to this s polynomial in all these proofs with x unknown, and then we're going to open it at the correct x's and for each of the commitments. And then, so the verifier can go on and evaluate the rest of the proof, and if it checks, they're happy. But the S1 and S2 and S3 and so on, commitments need to be checked to ensure that they're correct. So in order to do this, we use a trick where this helper is going to commit to all the S polynomials with x unknown. Then the verifier is going to sample z, and the helper is going to commit to the S polynomial with z, but y unknown. And so as a result, if you evaluate the C commitment, if you open the C commitment at each of the y's, they should equal the same value as the original commitments opened at z. And then all we have to do is check to see if the C commitment is correct. And so we have to perform an evaluation of the S polynomial once. We basically sample some random y, have the prover open it, and then we evaluate it in the field, and if it's correct, then we're happy. So that's really cool, actually. I think this is probably the most motivating part of our paper because the marginal cost of verifying a proof is actually constant. So that's really good. In order to actually call SONIC a SNARK, we have to somehow get full succinctness. So we need somehow for the verifier not to do a linear number of operations, even for a batch of proofs. And so what we do is we figure out a way to outsource the evaluation of this polynomial. So I'm just going to break this polynomial down into a couple other ones, this s prime and this s double prime polynomial, and so we can just kind of rearrange the terms, and we end up with the same thing, just looked at a little bit differently. What's interesting is this s double prime polynomial is basically just, when you look at it the right way, is just the sum of some polynomials of the form x plus x squared plus x cubed and so on. But this is actually really easy for the verifier to evaluate itself. You just have to perform sort of a logarithmic sequence of multiplications, additions, and squarings in order to do this. So that's not too hard. The real hard part is this s prime. So we need to outsource the evaluation of this s prime polynomial to someone else. Not necessarily the prover, but anyone else. So this s prime polynomial can be seen in a different way. It's essentially a bunch of terms where the exponent of x corresponds to one of the wires, the exponent of y corresponds to one of the linear constraints, and the coefficient corresponds to the coefficient for that wire in that linear constraint. And so we can actually beat this s prime polynomial into a different form for all circuits, where essentially it's expressed as the sum of a bunch of different permutation polynomials. I say m here, but as long as m is 3, then there's a generic reduction for doing this for all circuits, which I don't have time to get into, but I posted on Twitter how to do it, and you could read the code. So individually, these permutation polynomials, if somehow we can outsource the evaluation of those, then all we have to do is have someone commit to them with x unknown, then evaluate at the correct, or have them open it at the correct x, and then sum it up, and then we've done it. So just like before, we have to somehow check that these SJ commitments are consistent with what they should be. So just as a simple example, here's an example polynomial of this form where we're trying to check to see, is P really a commitment to this polynomial? So what we're going to do, because A and B are fixed, Y is also known to the verifier, but it's only known after, before this verification procedure takes place. So the verifier is going to pre-compute the these particular commitments using A and B being fixed and the fact the permutation is fixed. And then the prover is going to compute this P prime, which is basically the same polynomial as originally, assuming the prover is honest, except with the exponents of y correspond with the exponents of x. So the coefficients have been kind of shuffled around before the permutation has been performed. And we can check to see if this P prime polynomial commitment is actually correct, because if we open it as some random z, and then we check to see if the value that it opens at is the same as the value that this pre-computed A evaluates at yz, then we know that the prover is actually committed to the correct polynomial. Now, having done this, what we do is we check to see, has this permutation been applied correctly? And the way I like to think about it is we've essentially added, or what we're going to do is we're going to add some random stuff to all the coefficients in the first polynomial commitment, and add the corresponding, after the permutation, add the corresponding kind of random stuff to the correct coefficients of a different commitment in order to see that they did it correctly. So here we compute using the fact that our polynomial commitment scheme is additively homomorphic. We take P prime and add alpha B and add beta C, and we end up, we know because we know P prime is correct, that we end up with a polynomial commitment that looks exactly like this. This is before the permutation has taken place. And so, assuming the prover is honest, then this P commitment, if we add it to alpha D and add beta C to it, then we'll end up with a polynomial which has the coefficients in the correct spot, where everything's consistent and so forth. So if they weren't honest, then one of the coefficients will be different, basically. And so then we use the fact that if the product of all of the coefficients of the first polynomial is the same as the product of all the coefficients in the second polynomial, then we know that the permutation took place correctly. So this leads to a different argument that we have to do. We have to somehow prove that the coefficients of a committed polynomial are the same as the coefficients of another committed polynomial. We're going to assume that the polynomials are well-defined. We can ascertain this with the polynomial commitment scheme. And we also assume that all the coefficients are non-zero. This we get for free for the fact, just the way that we've done the change to the commitments. So the way it works, it's just a simple example. We have this P polynomial. And in order to prove that we know that the product of all the coefficients is a certain value, we're going to use some of the same techniques that we use when we're actually constructing our main argument with the proof of knowledge. So with the kind of circuit-related stuff where we have some multiplication gates. But actually, we're going to change it around a little bit so that we're going to have this C vector, and we'll have this A vector, which again just consists only of non-zero values. Now the C vector is overdetermined, and we know that Cn, the last value in C, must be the product of all of the values. Basically, all the C vector is a running product of all of the elements of A, and so we end up with the last value being the correct product of all the coefficients, which is what we want to prove is the case. So we use the same techniques as before, where we kind of collapse all of these constraints into a single equation, formal indeterminate y, and then obviously this helper, not necessarily the prover, is going to commit to this polynomial, the C polynomial, which we can rescale to move around, because if we evaluate it naively, we get C1, C2, but we kind of want to move it around and change some values in it as well. Notice that the prover is not going to be committing to the last value. We're going to substitute that in the equation later. So we use the same techniques as before. We have this P and the C commitment to the P and C polynomials, and then we introduce a new polynomial where it's been designed so that the constant term is equal to the left-hand side. If you were to take this equation and set it equal to 0, then it'd be the left-hand side, where V is the claimed value of the product of all the coefficients. And so just you applying the same techniques, boom, you have this grand product argument, and you have a SNARK. You get a SNARK from that. You have to do all that, but you get one. So now you might be wondering, well, where's this magical polynomial commitment scheme that is succinct and does all this? Well, there's one that we rely on that Kate et al. Published many years ago. Basically, we have some structured reference string where some x is embedded into the structured reference strings, various powers of it, and then in order to commit to a polynomial, this is a pairing-friendly group. We just evaluate a linear combination of the elements and the parameters to essentially evaluate the polynomial at this x, which is presumably unknown. Then to open it, we prove that we know a quotient polynomial, this p of x minus p of z, which divided by x minus z, which we know, which we can only know if p of z is really actually the evaluation, or that is the correct evaluation, because p of x minus p of z has a root at p of z, so it must be divisible by x minus z.